Okay, welcome back. So there was an example last time that I kind of rushed. So I'd like to start from scratch, okay, about joint distributions. So what was the example? The example was that we have a random vector xy with values in R plus cross R. And the joint distribution, or the distribution of this vector, so distribution of the vector, is given as follows. Let's call it nu, okay, or pi. It is given in the following form. So c e to negative cx dx e to negative y squared over 2x divided by square root of 2 pi x dy for x positive and y real. First of all, what's the meaning of this? The meaning is that nu is of this form, pi is of this form nu cross k, where nu is the first part and k, the kernel part, is the second part. And since this is the distribution of an exponential random variable with parameter c, we know that this is a probability measure, right? This integrates to 1. And this is a transition probability kernel because when you fix x, this is the Gaussian distribution with parameters with mean 0 and variance x. So we also know that when we integrate this from minus infinity to infinity over y, this is going to give us 1. So we know that this is a probability measure, and this is a transition probability kernel. So if you like to calculate the probability that xy is in a set A, where A is a Borel measurable subset of this product space, you can calculate it by integrating this expression, so kx dy. Let me write it this way. You can write it as nu pi dx dy. And this has this formula. So in particular, if you have a measurable rectangle, x is in D and y is in F, you can write it as a double integral, right? So integral of the kernel part over F, and then this times nu dx, integral over D. So this is for A, which is Borel measurable on this set. And this is for D in here and F in here. So all I did is to rewrite what we are given, right? This is the meaning of This is the meaning of what we are given here. It's the joint distribution of x and y, or simply the distribution of the vector xy. So one question we can answer very easily is the distribution of x. Okay? What is the distribution of x? Well, for this, we can just look at the probability that x is in some set, and then y is simply anything. So if you want to kill the second variable, this is what you can do, right? So now it's going to become an integral of this expression c e to negative cx dx. So this is Gaussian distribution with parameters 0 and x. Therefore, this integral is 1. So we get that this is equal to this. So this is, in fact, the probability that x is in D. So we conclude that x has the exponential distribution with parameter c. And so c was just a parameter, which is positive. So indeed, it is the same way, the same calculation that you did in maybe some undergraduate probability course, right? Whenever you're given the joint probability density function, what you do is to integrate it with respect to one variable to get the distribution of the other variable, right? Other component. So this is indeed what we do, but in a slightly more sophisticated way. But the calculation is the same, right? So the more interesting question is the distribution of the second component, y. Okay? Let's try to calculate the distribution of the second component. So in other words, let's look at x in R plus. Let me write it this way. So we're interested in the distribution of y. So we're going to take one set, f, and we can certainly write it as x is something and y is in f. So x is something means we integrate over R plus, integrate over f, the kernel part, and the measure part, the exponential part. So this is just applying the definition, right? So now how can we evaluate this integral? So since this set f can be quite ugly, we have no hope to get something nice for this integral, right? It can be just an arbitrary Borel set. And we also want to have something of the following form. Maybe dy. Because if we have some expression here, if we can write it down in this form, we would conclude that this is the probability density function of y, right? So to be able to do that, we have to swap the order of integration here. But we have a kernel here, and we have a measure here. How can we do that? So our Fubini-Tonelli theorem was only for product of two measures, right? Not for the product of a measure and the kernel. So how can we apply it here? Can you see this as a double integral, an integral for the product of two measures? Which two measures are in product form now in this integral? Which measures are in product? So which measure do I use in this integral? Which measure is this? Yes? Well, this is a probability measure, right? But unfortunately, here in this part, I have a kernel, right? So I cannot directly apply, if I see it as the product of this measure and this kernel, I cannot apply Fubini's theorem. Can I look at the picture? Can I look at it in a different way? This part? Of course we can, yeah. So we can, yeah, just write it here maybe. So forgetting about densities and so on, which measure do we have here? You have the exponential distribution, but it is absolutely continuous with respect to which measure? Which measure do we have here? Not necessarily a probability measure. So this is an integral of a function with respect to some measure, right? Which measure? I'm not going to answer this question for you. So we can just spend the whole hour just thinking about this measure. Which measure is this? When do we write dx? Which integral is this? Yeah, so Riemann means which measure? Lebesgue measure, exactly. So this is just one Lebesgue measure, and this is the other Lebesgue measure. So forget about all those densities, right? Forget about those functions here. So treat them as functions. Treat them as functions. And what we're doing is to integrate this function with respect to Lebesgue cross Lebesgue. So if I see it this way, I can apply Fubini. Everything's positive here. Those functions are all positive, right? So now we can apply Fubini for Lebesgue cross Lebesgue. OK, so now this is an integral over f dy and integral over r plus, let me write it as 0 to infinity, of everything about dx. Well, here, everything's about dx. This depends on x. This depends on x. So good, whatever this is. So if I call it just, so this is going to be a functional y, right? It's an integral with respect to the x variable, so it's going to be killed. So we're going to have a functional y. And whatever this function h is, this is going to be the probability density function of y, right? So I can just write h of y dy here. And the conclusion is that, so we did it for every f in the Borel sigma algebra of R. So the conclusion is that y dy is h of y dy. In other words, h is the probability density function of y. So, but of course, h of y is given as an integral, and we don't know what it is. So we can worry about that separately. So we answered the question, I mean, in a not very explicit way, right? We say this is the probability density function of y, but h doesn't look very nice. So we can try to find it, calculate it more explicitly. Can you evaluate this integral by some calculus trick? It's an integral about dx, but you have c times x, which is nice, but you have y squared over 2x, which is too bad, right? It's a very ugly integral. So I guess it is not very possible to calculate it using just ordinary calculus. So there are two ways to evaluate this integral. So the weird thing about this integral is that the ordinary calculus kind of fails, but still this is going to have a very nice expression. So not in terms of weird error functions or anything. So this is going to have a very nice expression, but we won't be able to calculate it using ordinary calculus. So ordinary calculus, let me say, fails until somebody comes up with a way to do it using ordinary calculus. But a well-known way of calculating this integral is through complex integration. So one way is to use complex integration. It's an integral of a real variable, but you can kind of see this integral as a complex integral and use complex calculus tricks to evaluate it. Of course, this is not in our scope. We're not going to do that. Integrals, integration. Another way is to calculate the Fourier transform, which we know, and see if it is a familiar one. You know, Fourier transforms of well-known distributions are usually collected in some tables on Wikipedia or some other website or in textbooks. So if you can calculate the Fourier transform of this, first of all, why Fourier transform but not Laplace transform? Because this is the PDF of a real valued random variable, not positive, right? So we need to go through Fourier transformation. So let's calculate the Fourier transform of this. So in other words, let's calculate this, okay, for every real r. So what is this? This is e to I r y. Let me write it this way. Cosine ry h of y dy plus I sine of ry h of y dy. So let's calculate it. This is from minus infinity to infinity. So if you look at this function h, it is an even function, right? Because y is squared, and this is the only place where we see y. On the other hand, sine is an odd function. So the product of sine and h is an odd function. So this integral is just 0. But what is this integral? Let's calculate this integral. So minus infinity to infinity cosine ry h of y dy. So we know h of y is given in integral form. 0 to infinity of this whole thing dx. And then we have dy. Okay. So again, we have two integrals. And we can use Fubini or Tonelli. So Fubini was for positive functions, but cosine can take negative values. So hopefully, this is going to be the case for, so we can apply Tonelli in this case, right? So what is the assumption of Tonelli? Tonelli says whenever this function is integrable, you can swap the order. So whenever you don't have infinity minus infinity, you can have this. So what is the integrand here? So you have cosine ry times all the other stuff. But this is less than just c times e to negative cx, e to negative y squared over 2x, 2 pi x, because cosine is between -1 and 1. And you can check that this is integrable. Integrable in xy. So integrable with respect to Lebesgue and Lebesgue. So we can indeed apply Tonelli. So if we do it, 0 to infinity dx, what is the part about y? So this is minus infinity to infinity, cosine ry, e to negative y squared over 2x, 2 pi x dy. We changed the order of integration. And now, hopefully, we are able to evaluate the inner integral. So what does the inner integral look like? Cosine times the Gaussian distribution with mean 0 and variance x, right? So can we evaluate this? Or have you seen this integral before? Cosine times the Gaussian density. Can you write it down as an expectation? Expectation about a Gaussian random variable. So if I want to see this part as the density, so this means this is my function of y, capital Y. Right? So let me write it as cosine r times some random variable u, which depends on x, where u of x is Gaussian 0x. Right? You know how to calculate expectations, right? So if you want to calculate the expectation of the cosine r times a random variable, you simply integrate this function times the distribution of the random variable. So if you assume that you have a random variable with this distribution, in fact, you can see this integral as the expectation of the cosine r times that random variable. And we know a formula for this because in one of the homework assignments, you guys calculated the characteristic function or the Fourier transform of Gaussians, right? So, so if you remember, the sine part was again 0. So this is, in fact, just the Fourier transform of ux. And this is, so some term about the expectation, which is 0, minus 1/2 r squared times variance. So this is by some homework 5, I guess. Yeah. So in fact, we can simplify this integral a lot. 0 to infinity c e to negative cx, e to negative 1/2. Let me write it as r square x dx. Right? So what is this? 0 to infinity e to negative c plus r squared over 2 times x dx, right? So this is c over c plus r squared over 2, which gives us 2c plus r squared for all r in the real line. So we calculated the Fourier transform of this random variable y. And now another question. So this is a Fourier transform, and have you seen such a Fourier transform before? Again, in a homework. So in that same homework, so by homework 5, probably the last question was that if you have a random variable, if y has, so let's say y has the Laplace distribution or the double exponential distribution with parameter, let's say a, if and only if its Fourier transform is given as a square plus r square. And the PDF of such a random variable, so by definition, double exponential means, so it is just like an exponential, but with a 1/2, because it is all over the real line, not on the positive part. So this is a e to negative a y in absolute value. So in other words, if you know that the Fourier transform of a random variable has this form, you make sure that it is a Laplace distributed random variable with this probability density function. Okay? So the conclusion is that here we can conclude that this y, our y, is Laplace distribution with parameter square root of 2c. So the density is given as 1/2 square root of 2c e to negative square root of 2c times absolute value of y dy. So we can also rewrite it as c over 2 in square root times dy. So this is our h. Okay? Final result is that x is exponential with c, and y is Laplace with square root of 2c. So I find this example quite interesting. For instance, this expression looks very hopeless, but apparently it has a very nice formula. and you calculate it through Fourier transforms. So we know now in principle how to calculate the marginal distributions of the components of a random vector if we are given the joint distribution of those components, namely the distribution of the random vector. But of course, this is only in principle. In practice, there might be a lot of difficulties in getting some nice formulas. But even if you cannot calculate this H explicitly, this still is a probability density function. You can still say that this is the probability density function of Y, right? It just turns out to be much simpler than this expression, but this is more of a simplification than the actual result. Okay, so I guess that's it about random vectors, but I just want to spend some time how to generalize those ideas to n-dimensional random vectors. It's going to be quite routine. So when you have multiple spaces, maybe 3 spaces, so let's say measures on finite products. For instance, let's look at 3 spaces, okay? You have E here with some measure nu. You have G, and now we have H. And we have one kernel from here to here, and another kernel from here to here. So this has one variable x and another variable f. And this has one variable y and another variable, which is a set in the 3rd space. I call it B. So we're going to define a measure on the product space by writing down nu cross K cross L. Okay? And I'd like to give a meaning to this expression by seeing it as the product of a measure and another kernel. So we have to define what K cross L is. So K cross L, it's going to be a composition in some sense. It's going to be a kernel from the 1st space to the 3rd space. So it has 2 variables. One is x, one is b. Okay. So we have to go from somewhere in the 2nd space to the 3rd space. This is fixed, right? This is fixed. This is where we would like to land in, and this is where we're going to start from. So the question is, in how many possible ways you can pass from x to b by stopping in the 2nd space? So if this is your position in the 2nd space, this is going to be the probability or the measure that you're going to end up at set B in the 3rd space. What we have to do is to integrate this over all possibilities for y. So that's an integral over the 2nd space. So I see it as a function of y, and I see this as a measure on the second space. So this is for X in E and B in H, and it is called the product kernel. Product kernel. So K cross L is a transition kernel from the first space into the last space. And now we can talk about this pi dx, dy, dz, which is given as nu dx k x dy l y dz. Or d cross f cross b. Okay. Or let me write for a general set. Just some set A in the product sigma algebra. So what do we need to do? We need to integrate this with respect to the last variable, and then second variable, and then the first variable. This is for all A in the product sigma algebra, right? E cross G cross H. And you also have, if you replace this with F, then this is going to be pi, FD pi. Sometimes we write it as pi F, right? Where F is positive measurable. So this pi is a measure. Pi is a measure. And I guess we need to assume something. For instance, that K, L, and let's say also pi are all, well, KL are sigma bounded and nu is sigma finite. Then this is also sigma finite, is a sigma finite measure. So if you remember the statements of those theorems about the product of a measure and the kernel, so this measure on the product space is the unique sigma finite measure assigning measurable rectangles certain values. So if you have that result if your kernel is sigma bounded and your measure is sigma finite. So to have a sigma bounded product kernel, you need to assume that the individual kernels are sigma bounded. And then if you multiply it by a sigma finite measure like this, that theorem applies and you get a sigma finite measure in the product space. So this is just the extension of the ideas for two spaces, to three spaces. And you can even have a more general construction with multiple spaces, just n finite, let's say. So, okay, this is going to be a strange picture. Let me draw it for 5 spaces, okay? Not to complicate it too much. So let me give those names to. So E0, E1, and there is a kernel from the first space to the second. well, I call it the 0 space, and this is the first space. So let's call it K1. So this is the kernel into the first space, okay? What we're going to do now is more general than what we did here. And the generalization is that now we're going to take a kernel not from the second space to the third space, but from the product of the first two spaces into the third space. So this is going to be K2 because I call it E2 script E2. And this one is E3, E4. Okay? So now this is going to be a kernel from the product of the first three spaces. So it's a very general construction of a measure on a product space. So this is K3. And finally, this is K4. Okay? So what do I mean by these? Let me be slightly more formal. So we have Ki, which is a transition, a sigma-bounded transition kernel from the product of, let me call it K, okay, let's make it I again. So J0 from I minus 1 of these first I minus 1 spaces into EI script EI. And news, so this is for I between 1 and n. And nu 0 is a sigma finite measure on E0 script E0. So we're going to call pi, which is the product of nu 0, K1, K2, Kn. In this picture, n is 4. There are 5 spaces, but since I started from 0, there are 4 plus 1 spaces. Okay? And you can define it iteratively, right? So if you have nu 0, K1, K2, K3, you can define those kernels, right? Or you can define it in one shot like this. So pi of A is defined as indicator x0, x1 to xn. So these are my variables now in all the spaces. So Kn is from x0 to xn minus 1 into dxn. Let me write it in color. The measure part versus the kernel part, okay? So let me use, blue. dxn, okay? So now it's an integral over the last space. Dot, dot, dot. So now it's going to be an integral. So K1, which is from x0 to x1. This is going to be an integral over the space 1. And finally, there is going to be nu dx0 over the space 0. It's a little bit hard to write it down, but it's a very general construction. So A is in E0 product up to En. So that's a more complicated dependence structure. And this is very useful in the construction of stochastic processes with memory, because later in a week or two, we're going to interpret those kernels as conditional distributions given initial positions. For instance, we're going to interpret this as the conditional distribution of this position, of the position in this space, given my position in the space 0. This is going to be the conditional distribution of my position in this space given my positions in the first two spaces, in this space and this space. So it is not like Markov chains, where all you need to know is the position in the previous space, but you need to keep track of your position so far, starting from time 0. Okay? So if you see it as time 0, time 1, time 2, your position at time 3 is going to depend, your conditional distribution of your position in the space 3 at time 3 is going to depend on your past, your positions in the time 0, time 1, time 2, etc. So you need to keep all the history so far. That's why we need to have more general structures, more general than this, okay, where you just have one-step transitions. So this is the setup for Markov chains. You just need one-step transitions, right? If you're given a question about Markov chains, what are you given? Just the transition probability matrix, right? And it is one step. And if you're given that, you can calculate all the n-step transition probabilities. But in general, this is not the case. You need to know all your past, and then you tell what your conditional distribution is.